Hello, and welcome to NET321. This is AWS PrivateLink deployments, DNS mechanisms for routing and resiliency. I see a pretty full room, so hopefully that title didn't scare anyone away, and everyone will get something useful out of this session. I'm James Devine. I'm a Senior Specialist Solutions Architect, and I focus in networking and VMware. Before we dig in here, what to expect from this session. This is 300 level, so hopefully everyone came with the base understanding of what PrivateLink is and what DNS is, domain name server. We'll dive into architectures and best practices. We're going to cover some of that basic material as well, just to make sure we're on the same level playing field before we get in and start talking about these concepts. The good news here is you don't need to be a network guru. In fact, if you know how to do an API call, you probably understand PrivateLink better than a traditional network engineer. And then adding on that DNS part to that as well, and just sarcastically, DNS is simple. All it does is resolve names to IPs. Anyone who's stood up a DNS server knows that that's not the case. But so the agenda here, we'll start with PrivateLink doing a quick overview. We'll talk about some updates. There's been some things that we've announced in the last year since I did the session on the best practices. Then we'll get into HA by design, Hyperplane. So one of the things I think that we haven't talked about too much is that we're actually powering PrivateLink with Hyperplane. So we'll get into some logistics of how that works and kind of open up the covers a little bit so you can see what's going on there and how we're achieving this high availability. We'll then get into a Route 53 overview and talk about what that looks like from within your VPC and what that looks like from outside of your VPC, and then go into some specific architectures and what the DNS looks like in those architectures, and then close up with some best practices. Starting out with PrivateLink. So there's a few concepts here. On the right here, just some general nomenclature. We have a service provider. This is where we stand up an NLB, our network load balancer. And then here on the left, we have a service consumer. This is someone consuming this NLB. And with PrivateLink, we're able to take an NLB and extend it into a VPC, which seems pretty simple at the high level, but actually there's a lot of pretty cool stuff going on here. So on this left here, I could have the same IP range as my VPC on the right. They could be duplicate, they could be overlapping. There's a lot of complexity that's just completely abstracted away because we're handling that packet flow at scale, and you don't need to worry about that. Also, we provide DNS, so you have easy resolution and a high performance here for your connection into the interface endpoint into your NLB. So high level, super simple, but really powerful. And we've seen a lot of customers use and build some really interesting application architectures with this technology. There's a few different consumption models, the first of which is AWS services. So typically our AWS services, being a cloud provider, they have public IP addresses and they live out on the public internet. So this works great if you're consuming them from an on-prem environment or you have public connectivity, but we increasingly hear from customers that they want private connectivity into these services. And that's where PrivateLink helps here. We have a VPC endpoint that lives within our VPC, your VPC as the customer, so you have access to that. It uses IP addresses that are resident within your VPC. And then through PrivateLink, we handle that stitching into the AWS service. So you speak directly to the PrivateLink endpoint. It looks like it lives within your VPC, and then that traffic gets routed to the AWS service. And this works at scale for a growing number of services. I mean, really, we want to have all services onboarded at some point, and that's something we're working towards. You'll see more and more services. Even over the last year, we've introduced a lot of AWS services that are powered by PrivateLink. There's two other consumption models here. Endpoint services. These are network load balances that you create and manage and then extend into other VPCs through PrivateLink, and also SaaS services. So we have a number of providers that you can go and provision a SaaS service, and they'll extend VPC endpoints into your VPC for you. And again, very similar consumption model here. We're just connecting in through the VPC endpoint through an NLB into an instance. And especially for like a SaaS provider model or endpoint services, I've seen a lot of customers that I've talked to that really just want services, and they don't want to have to worry about IP addressing them. They don't want layer 3 connectivity. You can imagine if this was on the right side here, if this was tens of hundreds or thousands of VPCs, that would be really difficult to connect to. And you could do it. We're adding scale with things like Transit Gateway, but you'll quickly find out that you just can't connect and you'll hit practical limits. Whereas with PrivateLink, we have that scale built in. The same technology we're using to provide our AWS services into PrivateLink endpoints, you have access to as a customer or as a SaaS provider. So getting into more of the meat of what a VPC endpoint is, and I see a lot of architects get this wrong, and I've seen a lot of diagrams that get this wrong as well. So when we talk about VPC endpoints, there's an actual VPC endpoint, and that is an entity. And what that actually is a collection of ENIs, elastic network interfaces. So it's one or more ENIs. There can be one per availability zone, and kind of shown out here in this breakout diagram. So this isn't a single point of failure. It's actually highly available, and we'll get into what that looks like from a Hyperplane perspective and what we're doing on the back end to make that highly available. But it's not a single entity. I've had some folks think that it was like, oh, it's an ENI and a server, and it's not. It's an entry point on our overlay network that allows you to connect into the PrivateLink service. So kind of a best practice here is you want to have at least one or more ENI, so you have that availability zone resiliency, and you can resolve and route your traffic to those different ENIs. Out of box, each one of these ENIs is capable of 10 gigabits a second, and that could go higher if you need. And if you have requirements for things like that, that's something we'd love to hear about and help you work through those architectures and make sure that we can meet those requirements. But out of box, it scales, and the VPC endpoint is multiple ENIs. Hopefully at least 2 for high availability, but you could have 1 in every availability zone. So like US East, you have upwards of 6, and scale out your performance that way. Getting to the DNS part of what this actually looks like, for an AWS service that's powered by an interface endpoint, when you go ahead and enable it, by default, there's this option to enable Private DNS for this endpoint. This will be enabled by default. And what this does is say you're going to our CloudWatch service, logs.useast1 for useast1.amazonaws.com. When you go and type in that IP address, you'll actually see that this resolves to a private IP address. So we're just taking this host name, and it's getting resolved directly to that private IP address. So we handle that for you all on the back end. You're not needing to route or configure anything. Within that VPC, any traffic that goes, in this example, to CloudWatch, goes directly to that endpoint. No public IP addresses, all private IP addresses that live within the VPC. We also round robin this. So if we go ahead and do NS lookup again, we'll see we get a completely different IP address. That's another ENI in that VPC endpoint. So we're able to round robin and have performance and availability that way built into the service. We also have the DNS names for all of these ENIs. And you'll notice these are public DNS names. If you were to go and plug these in, and actually this demo is still up, you probably would resolve right now to these private IP addresses. That's something you could leverage as well. The caveat there is when you use this public DNS, we're actually health checking. So if one of these ENIs, for whatever reason, wasn't able to serve traffic or wasn't healthy, we wouldn't resolve it and have that show up in the list. So you can actually address these directly if you had certain use cases where you wanted your data to stay within the availability zone and not have the ability or option to cross availability zones. But you should think through those architectures to make sure that you're planning for the appropriate availability. We can also, however, disable this. So we have it enabled by default. But this view doesn't exist outside the VPC. So there are some instances, like if you're trying to centralize your VPC endpoints, and we'll get into what some of those architectures look like, you might want to actually disable this functionality. Or maybe you don't want to use the public name. You want to use the private name that we provide for that endpoint. So that's an option as well. So we can see we still get a DNS name here. And that still gets resolved to a private IP address. We just have the ability now to create something like a private hosted zone or some other way to resolve to this endpoint. And we'll have some architectures that go through that. And then we also, again, still have our ENI for each of the endpoint ENIs have their own DNS name as well. Another consideration here is cross-zone load balancing. So on the network load balancer here on the right, so when you provision network load balancer, by default, we disable cross-zone load balancing is not enabled. You have the option to go ahead and enable it. And what this does, if you're providing a service, you don't have instances in every availability zone. So like here, I have instances in availability zone 1 and 3, but none in 2. And it might be an active-passive type of architecture or something that just doesn't lend itself to have instances in every availability zone, or it's just not economically feasible to have instances running in every availability zone. We could add a new availability zone and you not have instances there. So in this case, I mean, when we're going through the same availability zone, when our service consumer is accessing our service, everything works great because it's in the same availability zone. Now, if we have another instance here that comes into this ENI here, there's no instances here. So what would happen is if we didn't have cross-zone load balancing enabled, we wouldn't actually be able to have an ENI here, and we wouldn't be able to connect into the service. We'd have to use one of these other ENIs. But because in this case we've enabled cross-zone load balancing, we can access an ENI and then talk to our instances in another availability zone. So this is definitely something to consider as a service provider, or as you create endpoint services and extend them out. You may or may not want to do this. So there are, here there's going to be cross-zone AZ traffic charges, which I mean, in the grand scheme of things are probably trivial, but could add up depending on what you're doing at scale. So just something to think through as you're on the provider side creating private link endpoints. Some new features, endpoint policies. So this is something that, since we've launched PrivateLink, we've had the ability to create an IAM policy for an endpoint. It's just empty and allows all access by default. But we have a growing number of services that support endpoint policies, and these allow granular control over access to the service. So it's actually a pretty cool thing we can do here. This first example is for our API gateway, which we've added recently. So we can say you can invoke only these 2 APIs, and we call out the APIs. So doing this, we have really fine-grained control. Just because we have in this case, an API endpoint interface endpoint, that doesn't mean we have access to all private APIs. We actually can lock it down to specific APIs, and then we can further lock it down to specific actions. Maybe we want to get really granular with what you can actually access through that endpoint. So we allow you to have that control and really fine-grained at the network layer, and through IAM policies, you can audit and control these type of interactions. Another example here on the bottom is using code commit. So you can imagine an example where you have production servers and they're doing a pull from a Git repository, but we don't ever want them to be able to push. We can here say that we deny explicitly the push command into this code commit repository. So we're able to, again, really have fine-grained control access and provide an endpoint and not provide unfettered access to a service. We can start to lock down and control what we can actually access from that service. Another option is security groups, which not anything new, something we've launched with. You've been able to do this. So this is for traffic coming into an endpoint. You can control what can actually access it. If you don't choose anything, like in this case, it's just a default, because this is just a default interface endpoint that I created and didn't select that. I could get sophisticated here and make my source be an IP address. Maybe it's my web servers or my database servers, and I want to be able to log everything and have them access CloudWatch through my interface endpoint, and then not have the rest of my VPC have access to this endpoint. We can do that through security groups, in addition to the IAM permissions and the endpoint policies. Another option here that we've recently added is tagging. So just like everything in AWS, you expect to be able to tag it, but that wasn't something that we had out of the gate. So this is something we've recently launched. You can now take your endpoints and put tags on them. So in this example here, I've had a key of environment, and I called this one dev. So I can see I filtered here on environment now. So I have this ability now to go through, start tagging endpoints. Maybe you want to do it by environment or some type of endpoint, and use that for management and how you manage or even billing. But also control. So you can start creating policies and say, if the endpoint has this tag, you can or cannot take these actions, and applying a security wrapper around this tagging, just like you would with other resources as well. I'm not sure. I'm not sure. I can check, but I'll take questions at the end. I'll have some time at the end. So this quote gets used a lot. Everything fails all the time. I like it. It's not to say that you shouldn't trust things, but at scale, things just fail. I can tell you, I'm the type of person, when I was in deploying infrastructure, I would go into the data center and start pulling cables and pulling power supplies and just seeing what would happen if something died. And I always encourage customers to do that when they design and build, especially on AWS. We make that easy to do. But you should plan for that failure. And the way that we build services at AWS, we plan for that. So Warner Vogel said it best: everything fails all the time. Which is why we get to the architectures that we design, like Hyperplane. So this is something we started to talk about publicly about 2 years ago. This is public. If you have a network load balancer or a NAT gateway, this is all powered by Hyperplane. So this is how we're able to take our flows and scale them out and provide performance and availability. So if we look at what this looks like, and we've talked about this in other talks as well, so if you have a physical host, we need to be able to talk out over the network. So you're obviously, like any network, you have your IP packet. It's a standard IP packet. We then need to take it and encapsulate it in something that we can use and have a multi-tenant environment, and that's where VPC comes in. That's our overlay network. So we put a VPC encapsulation on that packet, and then obviously give it an IP address so we can route it around the network. Where Hyperplane comes in, especially in the case of PrivateLink, is having a fleet of servers that we can direct this traffic to, and then manage that and scale and route that traffic. And that's on the right where we have the Hyperplane nodes. So the Hyperplane makes transactional decisions and shares state in tens of microseconds. So this is designed to be super fast, super high bandwidth, and have that state built in, so we're not creating any single point of failure. So again, this is all within an availability zone as well. So when we're talking this Hyperplane infrastructure, this exists within an availability zone, and it's stamped out across every availability zone, which is why it's super important to make sure you have that ENI in every availability zone so you can take advantage of this high availability that we're building in and scale that out. So one of the ways that we achieve availability and performance is shuffle sharding. So the Hyperplane is it's a multi-tenant environment, so we have multiple customers that leverage the same fleet of servers. But what we do is when we allocate, so say you were to launch an interface endpoint right now, we would pick a set of Hyperplane nodes using a random algorithm, and then you'd be assigned those nodes. For example, here, in reality, it's certainly more than the 8 nodes that are shown here, but we allocate in this example just showing 3, and we'd give you those nodes, and those would be what would route your traffic. The advantage here is there's excess capacity. So if it turns out you need more capacity on the back end, we can grow and add you and allocate more nodes, or shrink or move traffic around. So it allows us to move traffic around and add performance in ways that aren't your traditional mechanisms of routing or doing IP type of networking. Now let's say another customer comes along, or even in your own account, you launch another interface endpoint. So in this case, we're given 2 nodes here and here, and there's an overlapping node. So actually, the way that this algorithm works is we're able to ensure that there's a very low probability that there's one overlapping node between customers, and as we scale out and at scale, the way that the self-sharding algorithm works, it actually becomes really low probability that one customer could have effect on another, which is what we'd want. We wouldn't want in a multi-tenant environment one customer having a bad day or one customer experiencing a high load to have a negative impact on another customer. This also further allows us to scale things out and add availability and move around traffic as needed. So hopefully that was a good overview of Hyperplane and some of how we manage that scale and availability. And this is all going on the back end, aside from anything that you need to do. You don't have to take any other action aside from making sure that you're leveraging multiple Elastic Network interfaces. So the process of doing that adds that availability, and that's within an availability zone. The way that we actually address and get to these ENIs is through Route 53. So that we'll cover in now. The main component here is the Route 53 resolver. So people have been familiar with this from a number of different names. We've called it the Amazon provided DNS. We've called it the .2 resolver. Since about midway through the year, we've standardized on the Route 53 resolver, so that's collectively, you'll start seeing that nomenclature especially when you read our white papers and blog posts, that's what we're referring to that as. It's a recursive DNS server, and our instances can just leverage that server by accessing the .2 IP address. But even that is slightly a misnomer. If you do your networking where you have a smaller than a /24 network, it might not be actually the .2 resolver, fun fact. But this has built-in resiliency. So this isn't a single point of failure. It's not a single IP address. It's actually the way that we route traffic and get it from your instance making the request into the Route 53 service, which I think is an important point. And especially with some of the improvements we've made with endpoints, we can get around having to do things like modify DHCP option sets and provide other mechanisms for DNS. Which gets into Route 53 resolver endpoints. So this provides the ability to have the same view of DNS that we have in our VPC and extend it into our on-premise environment, and vice versa, to have the same view of DNS we have on-prem and be able to extend that into the cloud. The way we do it for extending the cloud view onto prem is conditional forwarders. So our on-premise environment can talk to an inbound Route 53 resolver endpoint, and the way that you do this is just a conditional forward for the private hosted zone. This allows you to be able to resolve in the VPC as if your on-premise servers and DNS infrastructure was sitting in an Amazon VPC. We can also do the inverse with an outbound Route 53 resolver endpoint and a rule in our RAM resource access manager we could share out at scale. So we might want to resolve our corp.internal domain to our on-premise servers. So we can do that through an outbound Route 53 resolver endpoint and have that hybrid view of DNS both ways. And then this allows us to move our DNS management. So if we wanted to have private hosted zones in our shared services VPC, we can have those in that VPC and have that resolve on-prem and between VPCs. This has built-in redundancy. It leverages the Amazon Route 53 service. Also, with our outbound endpoints, they function very similar to the same way that VPC endpoints work. So you can provision multiple elastic network interfaces and build out scalability across availability zones in the same manner. So going through, I wanted to do this example myself, so I set this up in my own environment. I think it took me longer to set up a DNS server on Windows than it did to actually create the rule. So if you go in to conditional forwarders under the Microsoft DNS, there's the ability here to just specify the name, and here going through it, the same example, logs.useast1.amazonaws.com. I then add in the IP addresses of my inbound interface or my inbound Route 53 endpoints and clicked OK. And now I have conditional forwarding. So pretty simple to go through and set that up. And not to leave the Linux folks out, we also can do the same thing with named if you're using a Linux name server. So you just go in, you create the zone, and then you put in, specify the type as forward, and then specify the forwarders. Here I just did 2. This could be more. It could be 4, 5, 6, depending on how many ENIs you want on your endpoint. So pretty simple to set this stuff up and have the DNS forwarding. So getting into more of the private hosted zones, in the previous example, when we enable the private DNS for an endpoint, that works great within a VPC. We can resolve from within that VPC in and out all day long. That private hosted zone is actually hosted by a service VPC that's outside of your customer VPC. So we don't actually have the ability to attach that or extend that into other VPCs. So there might be examples like for VPC to VPC communication where you want that resolution through peering, transit gateway, or other type of architectures. For your interface endpoints where this doesn't work, and this is kind of digging in on some content. I have a blog post up if you want to see what this looks like more specifically, but we'll definitely talk through the architecture here. We can actually disable clicker died. can actually disable that, and then go into and create a private hosted zone in Route 53. So we just make it a private type, and then we put in the full name of the service. So in this case, log.useast1.amazonaws.com. Put in that service name. And then we can see on the right-hand side here, we can add VPCs. If the VPCs exist in different accounts, we can do it as CLI call or an SDK call and have that private hosted zone associated with that VPC. From there, we can then create an A record, and here we're doing an alias. So the magic here with an alias is you typically can't have what's called an apex record for that very top level domain and have, or that very, it's called the naked domain, so the very root, you can't have a name. With an alias record, though, we can actually add in A records, and we'll resolve just the way we did before, where we round robin between the endpoint names, and then our alias target is just the endpoint itself, and then we'll handle on the back end making sure that that maps to the right IP address for the interface endpoint. We've covered some more of this in our hybrid DNS white paper. This is something that we've updated. This has been around for a while, but we took the time and put in a lot of work to update the best practices to make sure that we're accounting for accounting for both interface endpoints, but also for the Route 53 resolver inbound and outbound endpoints and how all that data flows work now. So definitely a good resource there if you're looking to for some recommendations on the DNS side. Now we'll get into some architectures and talk through what the DNS looks like when you go through and implement these. So this first example, which I think often goes underappreciated, but the ability to extend on-premise services into a VPC. So in this example, having a central shared services VPC where we're able, it's not working well for me. Having a central shared services VPC where we're able to having a central shared services VPC where we're able to have endpoints where we're extending them into our service consumers. So this can be tens of thousands of VPCs, and we don't want direct layer 3 connectivity into our on-premise environment. So instead, we're going through an NLB, and our shared services VPC is the only VPC that actually has direct connectivity. Oh, man. It's not my day, and it's not late enough to go to the bar yet. Okay. So, picking up where I started. So, what we're able to do here is extend services that are living in our on-premise environment into our VPCs and do this at scale. So, again, there's no layer 3 connectivity here. We don't need to set up a transit gateway. We don't need to set up a complex routing. Really, the only thing that's addressable from our on-premise environment is our shared services VPC. We're then able to extend it and share out these services at scale. And this can be multiple NLBs in this shared services VPC, and then connecting to really complex architectures here over direct connector or VPN. So I think this is a pretty nice use case, and there's a number of situations where I've talked with customers, and this really was a good solution to be able to extend without providing that full addressability. Also, the way PrivateLink works is it's a one-way connection. So my services living in a VPC can connect into just that NLB and then connect into the backend service. There's no connectivity for on-premise to start probing in or reaching around. There's actually no connectivity for them to reach into the service provider or service consumer VPCs in this environment. We can also work in the flip side. So from an on-premise environment over direct connector VPN, reach into a VPC endpoint and have the only IP space that's accessible from our on-premise being that service consumer, and then from there connect into an NLB and then into our instances. And this really works at scale, so we can have multiple endpoints. These can be endpoints for AWS services, so perhaps in this example of using CloudWatch, we can have a CloudWatch endpoint, so we're talking directly into an endpoint in our service consumer, and we're not actually having to extend go out over the internet or extend an interface endpoint anywhere else. It works directly through this type of environment. And again, this is a one-way flow. So from on-premise, we can reach into this endpoint and then reach into our service. But our services have no connectivity into an on-prem. So it really creates a nice security model where we can extend all of these cloud services into our on-prem applications without having to provide that return path for data to flow back in. In this case, we're just using standard private DNS. So we provide, with every endpoint, we provide the resolution of those names, so you don't need to worry about anything there. For some of our services that are public, like in the example of CloudWatch, some of the things that we talked about with DNS and setting up private hosted zones, you might want to consider doing some of that, and we'll get into an architecture that walks through what that looks like. Another thing that we can do is cross-region connectivity. The product manager, in preparing these slides, made me put up this caveat, so avoid inter-region dependencies, and we'll talk through what that means. But the same way that we can talk through instances through an endpoint directly within a region, we can actually do that and extend connectivity into, in this example, US West. So from US West through inter-region peering, we can connect into a VPC endpoint in US East 1. So we've made a lot of improvements on the way and the way that we're allowing data flows over the last year. So these type of things can work and actually work quite well and leverage things like inter-region peering. Our DNS in this example, we're just accessing an endpoint with a public public DNS name that resolves to those private IP addresses. So DNS there is again still fairly simple. About that caveat about avoiding inter-region dependencies, this is a great way to start extending things and extending services into other regions or extending endpoints into other regions. But again, back to the example of how we're using Hyperplane and we design for all of this high availability within an availability zone and within a region. You really want to think twice about like just extending that and saying, well, we'll just add in yet another dependency. You're going to be able to achieve higher levels of availability and more resilient architectures by having the services close to the consumers that are using those services. So just something to think through as you build out architectures and think through your failure domains and your SLAs and how you want to have your disaster recovery and be able to respond to situations where things fail. Because again, things fail all the time, and adding in more dependencies just adds more complexity and more ways that things could fail. So extending on that concept a little further, and again, same caveat here about avoiding inter-region dependencies where you can. So within a region, we can connect directly, and that all works fine. We also have the ability here, though, to, on the top, we have US East 1. On the bottom, we have US West 1. We can extend an NLB into EU West 1, and then use IP targets on that NLB and access our instances over inter-region peering to the service provider, which happens to be in a different region. So this is a really great way for, if you're a service provider or you have a number of services, to extend NOB and VPC endpoints into another region without having to stamp out your full footprint. And I've talked with customers that had situations where it just didn't make sense. There was a requirement for 1 or 2 customers to start leveraging a new region, and it just didn't make sense to build out the full stack of technology in that region. So this allows you to extend that infrastructure and build out and still connect back to the core infrastructure in another region. I would say, again, caveat here is you're building this out, make sure that you're accounting for how things could fail or would fail, and performance, and doing your testing here, because we are creating a strong inter-region dependency where if something were to go wrong with one component that was completely outside the region, it could affect the service availability in another region. And again, it's not a paradigm that we use when we build services. We try to make sure we have strong regional isolations, and even within a region, we have strong isolations within availability zones. So a word of caution as you build through and think through architectures, certainly come and talk to us. I'm always happy to talk to customers about how they can build things out and what they could or should do. It's always interesting. Another thing we recently added is shared services VPCs. So you've been able to deploy an NLB and use IP targets, but the real new thing here is being able to have your NLB have instance targets in the same or different subnet within your account. So this is showing that shared services or shared VPC. So you can see, and I missed my clicker, I can't actually point to this. We have 2 accounts on the right that are leveraging this VPC. So we have an account for service A and an account for service B. They each have their own NLB with their own instances, and we're able to route traffic in and have multiple NLBs and multiple services all residing within the same VPC here. And this can go over Direct Connect or VPN to our on-premise environment. And in this type of architecture, having this shared services in the middle allows us, again, to have that single entry point where we have maybe a small subnet, maybe a /24 or something, where we have our VPC endpoints, and then they can connect back to a fleet of large numbers of NLBs and large numbers of services and scale out and build a highly available architecture without needing to stamp out direct infrastructure and having layer 3 connectivity to every other point within the architecture. Another thing that we can do, this is actually within the last year we've added this capability, is extending endpoints behind endpoints, which kind of seems like Inception, and you might ask why you would do that, which I found myself asking until I came up with a scenario where a customer actually needed this type of architecture. So having endpoints connecting through PrivateLink to an NLB, but then behind that NLB, having IP targets that are actually the ENIs of other endpoints. And in this example, for SFTP, it actually can make a lot of sense because we have this service that lives within a VPC. And if we want that SFTP endpoint to be shared out to tens or hundreds of the examples, in the one example I was working with a customer on, it gave them the ability to do that where they didn't otherwise. So there really isn't a way with SFTP endpoints today to share that out at scale with other VPCs. So you can use this and then provide endpoints to the endpoint and share that out and broker that out to other customers or to other VPCs within your environment. So kind of an interesting use case here. I could see other ways that this would work. From an availability perspective, we still have health checks on the NLB going to our endpoint DNIs, so we still maintain that availability there. And then we're using using the public DNS names of the VPC endpoint, so we have that resiliency and scale built in using the existing DNS infrastructure. So this is kind of putting this all together, like sharing VPC endpoints. So one of the things that you can quickly discover at scale when you start going and deploying endpoints is you pay per ENI per hour, so it can quickly become expensive to deploy this infrastructure and have multiple endpoints. Say if you have 10 or 20 AWS services you're using, if you were to put those 10 or 20 endpoints in 100 or 1,000 VPCs, that quickly adds up. So we can actually share out those endpoints. So up here on the upper right, having a shared services VPC, that's where we can place our endpoints. And then using Transit Gateway, provide that layer 3 connectivity to all of our VPCs, and then to on-prem through Direct Connect or VPN. And then again, sharing out that common view of DNS from the shared services VPC using an inbound Route 53 resolver endpoint that allows us to resolve those with conditional forwarding, be able to resolve those private hosted zones as if they were living in an on-prem environment and extend that into AWS. And on the flip side, we're able to use an outbound Route 53 resolver endpoint and still provide a hybrid view of DNS for your on-premise environments and have that hybrid view there. And our instances on the left, and we're only showing 3, a dev, test, prod VPC, but this could be obviously many, many more, being able to connect in, and they're just using the .2 resolver. And we can see at the top there that the lines for private hosted zone associations, that's providing the association of the Route 53 resolver to the private hosted zone. So pretty complicated picture, but pretty much everyone has the same view of DNS, so that allows us to place endpoints for specifically AWS and SaaS services in the shared services VPC and have that end-to-end resolution. Another thing kind of tying all of these DNS and endpoint principles together, I wanted to talk about Active Directory and hybrid DNS. So a lot of times, and if you go actually now onto the internet and look up our best practices, you'll see to set the DHCP option sets to be either your DNS IP addresses of your AD servers or to be the IP addresses of our Active Directory or Microsoft Active Directory managed service. That's still out there as ways to do that. We can actually do that natively with Route 53 resolver using resolver rules and share out the name for our Active Directory and provide that resolution without actually having to go and modify our option sets. And this increases our availability and scale. So we can see in VPCA in the upper right, we have aws.corp.internal. We can have a Route 53 resolver rule, and that you share out through RAM, the Resource Access Manager. That will point to the inbound Route 53 resolver endpoint. And within that VPC, having AD servers in our shared services VPC, we can then forward that to the AD servers. When we do that forwarding, we actually round robin between those ENIs in that inbound endpoint, and we can do up to 10,000 queries per second per ENI. So we can scale that out, and if we need more queries per second, we can just add in more ENIs. So being able to have that scale and that round robin, we also can avoid some of the common pitfalls of modifying the DHCP option sets. If anyone's ever done that before, you notice most of your traffic, pretty much all of your traffic, will go to the first IP address that you specify in that list, which is kind of less than ideal, especially if that primary server goes down. Then you end up getting a hotspot and all of your first tries at a DNS query failing. So we can mitigate some of those type of issues that are typically there. And then for on-premise resolution, again, we can have an outbound endpoint which resolves to our on-premise. So we get this hybrid view and kind of the best of both worlds. And this also, within the VPC, we're not forwarding things like if I want to resolve any service name.amazonaws.com, I'm not going all the way to my shared services VPC to resolve that and adding in latency and several hops. We can actually resolve that directly within the availability zone and not have to go into a shared services VPC and add in that extra hop and latency. Now I'll get into a few quick best practices. On PrivateLink, so you want to use at least 2 ENIs per VPC. You could use more. You can do up to 1 ENI per availability zone. So definitely do at least 2. It's easy to set that up and do that. Consider your DNS infrastructure. So we've talked through a few different ways you can build out your infrastructure and have your routing and set up your resiliency. Ensure your service provider NLB has an ENI in each availability zone. So this is just purely for discoverability. The way that we map availability zones, if you spin up one account, your availability zone ABC could be different from that other account's availability zone ABC, D, E, F. So there's not a one-to-one mapping. We have recently exposed ways to see that AZ ID. So you can, there's a console, you can see it in the console. You can also make an API call and see what that availability zone ID is. Just to simply avoid that type of issue, you can just, on the provider side, make sure that you have an ENI in every availability zone, and then make sure that you're enabling cross-zone load balancing so you have that connectivity to your services without a service consumer trying to spin up and not being able to provision an endpoint. Also, avoid building strong inter-region dependencies. So if you can run everything within a region and have your services up and running and not need to connect into another region to actually function, you only have a more resilient architecture. You could consider things where you'd fail over to another region or have your infrastructure be redundant in another region. I think I would really urge more architectures like that as opposed to building really strong inter-region dependencies. And also, that's just the way that AWS has been able to scale and build out our infrastructure. We don't build in these strong inter-region dependencies. So we'd like to beat home, even though I showed some architectures that could work and are supported, you wouldn't want the heart of your application to leverage inter-region connection that could extend outside of a region and have higher latency or more variable latency or other dependencies. For Route 53, since last year that we introduced the inbound and outbound endpoints, you really want to use that .2 Route 53 resolver. That's going to be the lowest latency, highest performing resolver you can use. So if you start doing things like modifying option sets, that adds additional latency and can create hotspots for your DNS. So really, you want to use that .2 resolver if you can. We call it the Route 53 resolver now. You want to avoid pointing outbound endpoints at inbound endpoints. There's some literature out there that says you should do that. You really want to avoid doing that. You're actually creating flows where you come in one availability zone and go out another availability zone, and DNS queries can kind of bounce around. So where possible, you want to avoid those type of architectures. There could be some reasons to do that. Definitely talk through that with your solutions architect, and we want to make sure that you're designing your application to be resilient and highly available. For your on-premise resolution, use conditional forwarding. That'll allow you to have that extend that DNS view that you have within your VPC without having to make your on-premise DNS servers authoritative for Amazon IP space and namespace. And then finally, you want to avoid A records to VPC ENIs. So you can actually address those ENIs. They have a static IP for that PrivateLink endpoint. But if you create an A name, there's no health check there. So if something were to go wrong with that ENI, or you needed traffic to move over to another ENI, you wouldn't get that. There could be architectures where you wanted to keep your traffic between your service and your infrastructure local. And certainly there are use cases where you could do that, but you want to avoid that, or at least consider what your failover is going to be and how you're going to route traffic. Instead, use alias records. Definitely use alias records, because we'll handle the mapping on the back end and the resiliency. Or you could use CNAMEs. So if you wanted to have a friendly name in your own namespace, you can have a CNAME to the endpoint. Some takeaways. PrivateLink endpoints are highly available. So hopefully showing the way that works with Hyperplane and the way that we design and engineer the traffic within our network was helpful in seeing that. Route 53 is both highly available and fault tolerant. It's one of the few services we have a 100% SLA on, so we pretty much guarantee it won't go down. And even in light of some things that have happened on the internet, it's always been up and running and chugging along. So it's actually a pretty resilient and great product to use for your DNS. And together, PrivateLink and Route 53 allow you to create some really novel architectures and hopefully ways that you can use and leverage. We do have some related content throughout the week. Some of this has already happened. NET321 is a deep dive on managing DNS across hundreds of VPCs. NET410 was a deep dive on DNS in hybrid by one of our principal engineers. That's, I'm sure, a great session. And then NET336 and SEC347, some of those I think have repeats going on. Those are builder session where you can sit down with some of our SMEs and work through building some of these architectures out. With that, apologize for technical difficulties. Maybe end a little early, but we have about 12 minutes left for Q&A. So if you have a question, raise your hand and we can get a microphone. Yeah, it's coming. No. So question was, does VPC peering go across PrivateLink? That's actually handled at the VPC layer within a region. It doesn't actually go over PrivateLink. Yeah, sure. So question was, if you're creating a new private hosted zone, does that association need to happen through the CLI or SDK, or can that be in the console? So if it's within the same account, you can do that, certainly do it within the CLI, or I mean in the console. But if it's outside of that account, you need to do it through the CLI or SDK. I would love to get feedback on that. Yeah, so that's something that I've made clear that we need a better way to do that through the console. Anyone else? Any questions?
Hello? A question here. How would inbound roles look like for multiple VPCs if I want to query from on-prem instances?
I'm sorry, what was?
How would inbound resolver rules look like for multiple VPCs queries in the AWS resolver rules? If I want to query from on-prem, if I want to resolve from on-prem the AWS DNS names, okay, what would be my conditional rules for multiple VPCs?
Oh, so the question is, how do you resolve the Amazon DNS from on-prem? Yeah, so what you could do is you could do amazonaws.com and forward that at the inbound endpoint and that would resolve. So that inbound endpoint can resolve, I mean, it can resolve out to the internet if you wanted to. It has the view of DNS that is local with that VPC. You'd probably want to do it regionally, though, so you don't create, you know, a multi-regional type of situation. But yeah, you can.
For rules. If I have multiple VPCs, I will have multiple .2 resolvers, right? DNS, .2 DNS resolver.
So is the question, can you use multiple rules with a single endpoint?
Not that actually. So if I want to query an on-prem DNS query, if I want to make a DNS query from on-prem, so I have multiple VPCs. When I have multiple VPCs, I will have multiple .2 forwarders, right? So how would my inbound rules looks like? Do I have to add every .2 IPs from each VPC?
So the way that the endpoint works is you have the same view of DNS. So for an inbound endpoint, anything that you can resolve from within that VPC, you can forward from on-prem and have that same resolution. The other way, anything that you can resolve from those on-prem DNS servers, you can create a rule to forward to on-prem. That answers the question.
Yeah, I think so.
Anyone else? Great.
Hello. I had a question regarding the Hyperplane.
Yeah.
Could you please explain me under the hood, is it the Hyperplane nodes or the sharding, is it within the same VPC or do you manage a different, I believe it's within the same region. Could you please give me more details on how it's running under the hood? The Hyperplane.
Yeah. So under the question is Hyperplane under the hood. So within that whole infrastructure I was talking about, that exists within each availability zone. So within an availability zone, we'll have a fleet of Hyperplane nodes, and we'll direct traffic to that fleet. And that's where that shuffle sharding comes in, where we put the endpoints and the customer across multiple of those multiple servers within that fleet. And that's how we achieve that high availability. And then that's repeated in every availability zone. We have that similar infrastructure.
Is it a same VPC, within the same VPC, or like different, same account or different account, how it is done? Like, I just want to understand how high available and scalable the Hyperplane is, because Transit Gateway and everything are using Hyperplane, right? So I just want to understand, you know.
Yeah, so the question is like how that works and what that actually looks like. So we don't typically get into the, under the covers, like, open up the engine and show what's in there. So it's interesting that we actually have been speaking about Hyperplane publicly and talking about how we think about and build services. What I will say is it's not, since we're operating at the VPC layer, so it's not like we're spinning up like a VPC per customer or anything like that. We're at a deeper layer of abstraction on the network path. So hopefully that answers the question. Yeah, so the question was about gateway endpoints. Gateway endpoints are actually different, so I didn't cover them to leave time for the other content, but gateway endpoints for DynamoDB and S3, they function differently. So they live within each VPC. And there's really not much use to centralizing them, because now you're paying data transfer fees for data transfer that's actually free within that VPC.
And that goes over the internet, that doesn't go through PrivateLink, right?
Well, so gateway endpoints stay within a region. We don't, yeah.
So if you want to use something going through the PrivateLink, like an application, does that affect like the MTU, since it's kind of going through the backbone, like that network MTU, like peering, you can only use 1500, and if you're local within a VPC, you can use like Jumbo 9000. Do you know if it affects the MTU using PrivateLink?
Yeah, so the question is if it affects MTU. So because we're taking that packet and encapsulating it, as long as that will fit within the frame, then it'll go around the network. I'm not sure actually off the top of my head whether we have MTU support. Definitely 1500 bytes will work. Larger than that, I could certainly get back to you on that.
Okay.
Hello. I have a question regarding interface endpoint. And my question is there a restriction on the number of security groups you can use I have noticed that is more than 5. Is there a limit? The reason I'm asking is, for example, we use namespaces basically across our teams when we use same VPC for security and IAM. And so I don't know how many security groups I can associate with that interface endpoint.
Sure.
Can
so the number of
everything use their own? Is there a limit?
Yeah, so I'm not sure the exact limit. Could certainly find that out for you. And if there was an upper limit that you needed, we'd work with your solutions architect to find out what's currently supported today and then what it would take to get where you need to go. Yeah.
Hello.
And that's where resource policies and things like that can come in as well to help restrict and control traffic.
Sorry. I don't expect you to be able to answer this, but any chance or any on the roadmap of S3 going with PrivateLink?
So I can't publicly speak about roadmap. You can imagine we want interface endpoints for more and more services.
Okay,
Yeah.
thanks.
If you're looking for more of a specific roadmap, definitely talk to your solutions architect and they can get that to you. That is a common customer request.
Do you have any recommendations around monitoring the health of PrivateLink endpoints and like throughput or health of specific AZs?
Sure. So monitoring the health of PrivateLink.
Yeah.
So if you're using the public DNS that we provide, we round robin between those names. So in terms of monitoring there, we're actually doing that for you, so you don't need to worry about it if you're using it that way. I think if you're building like regional services, and then that's where you'd need to get in, or within availability zone, you want to leverage that E&I directly, then that's where you'd want to monitor that health. I'm not sure off the top of my head the CloudWatch metrics that we do or don't support for that, but I could definitely dive in and look into that if you were curious.
Hi, my question is, why is the NLB an integral part of the PrivateLink? What's the architectural decision for always including that as part of the standard design for the PrivateLink?
Sure. So the question is why NLB with PrivateLink? That's just the way the underlying technology Hyperplane. So NLB is based on Hyperplane as well, and PrivateLink is as well. So being able to separate out the flows from the actual traffic, we can intelligently route it around the network and create these type of flows. I think longer term you'll see different types of options. Cool. On the left. Thank you for coming, and the diehard people that stayed for questioning at the end. Thanks a lot.